All right, so sometimes it's useful to decompose vectors, that is to break the vectors apart into a sum. This process is called the resolution of a vector into components. So projections allow us to identify two orthogonal vectors having desired sum. So let's kind of just write out, so here's our definition. The process of breaking a vector apart into a sum is called the resolution of a vector into components. All right, so they kind of talk us through this example here. If we're given our vector v, which has components 6, -4, and u has components 3, 1, we want to decompose the vector v into orthogonal components such that one of the components has the same direction as u. So let our vector v with components 6, -4, and our vector u have components 3, 1. Our goal is to rewrite v as a sum of two vectors, and in particular two orthogonal, right? Where one of them is in the same direction as u. Let's see how to get started with this. So the first thing that we're going to do is find the component that has the same direction as u by considering the projection of v onto u. So we will find the vector component in the same direction of u using our projection formula, the projection of v onto u. So let's go ahead and work through that with them. So P is equal to the projection of v onto u, which we know is defined to be the dot product of u and v divided by the magnitude of v squared times our vector u. So we're interested in the dot product of u and v divided by the actual magnitude of u squared. 3, 1. Times our vector u. Let's go ahead and compute this with them. We know that our numerator is going to become 18 minus 4, and our denominator becomes 9 plus 1 into our vector u, which is equal to 12 over 10. I'm sorry, 14 over 10, my mistake, which simplifies to give us 7/5. So once we do that distribution, we're going to get 21 over 5, 7 over 5. So this is our projection of u onto v. So this is one of our components, and in particular, it is the component that is in the same direction of v. So the component of v, which is in the same direction as u. All right, well, we would like the two vectors to add up to give us our vector v, right? So based on our properties of vectors, all we really have to do is take the difference of our vector v and p, and that will give us the other component. So step 2 is to find the second component, we're looking for Q, which is equal to V minus P. All right, so our second component equals our vector V minus what we calculated up above. So our vector V was 6, negative 4. And our vector P, we just calculated, is this 21 over 5, comma 7 over 5. So when we compute those differences, let's see, we're going to get divided by 5 is 30 minus 21, which has 9/5. And then negative 20 minus 7 is negative 27 over 5, corresponds with what they received. So this is our second component. All right. So this is orthogonal to the first. So let's actually prove that they're orthogonal. How do we know something's orthogonal? Right? Well, we had a rule that says if the dot product of two vectors is 0, then we're orthogonal. So if we calculate the dot product between them and get 0 for P and Q non-zero, then they have that orthogonal property. And I know we're not actually using this notation in this class, but I think it's pretty consistent. So let's test it. Our first vector was 21 over 5, 7 over 5. And our second component was 9 over 5, comma, negative 27 over 5. So let's test it. So 9 times the 21 is going to give us 108. 189. What did I just do? Divided by 25. And then 7 times 27 is 14 plus 49, negative 189 over 25. And sure enough, we get 0 just like we should. Fantastic. All right, so let's actually work on an example through our own